Hi everyone, welcome to lecture 11. This lecture is on energy. It's a new topic and it's a joint lecture between both the calc and the non-calc students. So we're done studying Newton's laws and we're going to move on to a new topic of energy. Energy is, and conservation of energy is actually derived from Newton's laws. And so it's not that it's a new type of physics, it really is Newton's laws, but it's Newton's laws converted in a way that makes problem solving much more easier. And the reason for that is that this is a conservation law. So I need to explain to you what a conservation law is. Uh, Newton's laws themselves don't explicitly show the conservation law, but they contain within them all the logic that leads to the conservation law. So here's an example of a conservation law. Say we were in a classroom and we had so much cash in our pockets and we're allowed to exchange money between one another, but no one's going to leave the classroom, no one's going to enter the classroom. All we're going to do is just keep exchanging money between ourselves. Maybe we're doing some kind of trading back and forth, and this can continue for a while. Trading, I give you $10, so my total amount of money decreases by 10, but yours increases by 10, and so on. Okay, and we just keep doing that. At any moment during this trading, if I were to ask the question, how much money is in the room, that total amount of money would remain constant. Okay, and so what that does, that fact that the total amount of money is constant, what that does is it constrains where the exchange is going to go. You can't just have any old exchanges going on because money isn't going to be created and money isn't going to be destroyed. It's always going to remain a constant amount. And these conservation laws, because they add this extra constraint, make solving problems really easy. In fact, there are problems that you wouldn't be able to solve without using these conservation laws just because of their difficulty. Okay, and so we're actually going to study some other conservation laws too, like we're going to study conservation of momentum as well, and conservation of angular momentum. And so again, these conservation laws are very important. They open up an entire class of problems that you otherwise would have a lot of difficulty solving. So let's start off there. Let me try to show you a type of problem that you could in principle do using Newton's laws, but you would find very difficult to do. Okay, so let's start off with a roller coaster. Take a roller coaster. Okay, so up here you have this roller coaster car, and it's the top of the roller coaster, and it starts off with an initial velocity v naught of 0 meters per second. So it's just sitting here at the top of this roller coaster, and it begins to roll downhill, and it goes downhill and then uphill and then downhill, and it gets to the bottom here. And I ask a very simple question: how fast is the roller coaster going at the bottom of the hill here? Now, if you were to use Newton's laws for this, you would have to basically calculate the velocity or the acceleration at every point along the entire path, because the acceleration isn't going to be constant. Okay, when you're on a flat slope like this, there's very little acceleration. When you're on a steep slope, there's going to be a lot more acceleration because of the component of gravity tangential to the path is going to be bigger when it's steeper. And so there's a lot of little acceleration, then a lot, and then there's none. And that's actually in here, there's going to be deceleration, then no acceleration, and then a lot of acceleration there. And so you'd have to go through every single point along this and actually calculate that. And then at the very end, you would get the velocity. And of course, to get the acceleration at every one of these points, how would you do that? Well, you would use Newton's second law. You'd have to calculate the total force, the net force, on the car at every single point. Okay, and that would be a vector sum of all the forces. And just ignore friction to make life easy. You would have the gravitational force down, and you would have a normal force, and that would be it. And you would just calculate that total force, and then from that you would get the acceleration. And from the acceleration you would get how much the velocity changes at every point along this path. Okay, and one of the things you realize when you do this problem, not only is it difficult, but I got to give you the details of this entire path here. Okay, it actually turns out that this problem can be solved without knowing the details of the path, which is amazing. Okay, like all of that work that you would have to do to calculate the acceleration at every single point is actually unnecessary. And so that's what I'm going to try to convince you of. Now, how would we do this? So suppose I did throw this at you and I did give you the details of the path, and I say, look, all you have are Newton's laws the way we've been applying them up till now. How would you go ahead and solve this problem? How might you do it? Well, uh, the fact that this is a curvy path causes a problem. So you know what? As a first approximation, let's just say, you know what? I'm going to take my curvy path and I'm going to break it up into a bunch of straight line segments, okay? So, I know this isn't the same curvy path, but just imagine, here I am, I travel some distance along a straight line as I'm going down this roller coaster, and then I turn, well, not turn, but, I go at a steeper angle, and then I go up at some angle, then I go down at some angle like that. And here I've taken the curvy path and basically broken it up into 4 line segments. Okay, so like one line segment there, another one there, another one there, and then another one there. Okay, not perfect, but it's a start. Okay, well, each line segment, if you look at it, each line segment is basically one of our little wedge problems, okay? And so you could redo the inclined plane problem at, along the first segment there, and then you would do an inclined plane problem along the second one, the third one, and the fourth one, and then finally at the end you can get the velocity. And the way you would connect them together is, you would start off, say, with 0 velocity at the top. You'd find the acceleration during the first inclined plane, okay? And then because you know the length of that, you would find the velocity at the bottom of that inclined plane. So you'd have the velocity there. But the velocity at the bottom of the first inclined plane is the initial velocity at the beginning of the next inclined plane. And so you could get the velocity that you end up here, that's the velocity that you start with there, and so on, and you tie them all together, okay? A lot of work, I agree, a lot of work. But let's just pretend that we're going to do that, okay? So to start with, I'm not going to do 4 here. I'm not even going to try to approximate our roller coaster track. All I'm going to do is just consider 2 inclined planes like this, okay? So I have plane number 1 here, okay? And you can see here I've got my car. I'm just going to draw it as a mass M block like that. And here it starts off with some initial velocity v naught, all right? Maybe 0, maybe not, it doesn't matter. It just starts off with some initial velocity v naught. And by the time it gets down to the bottom of plane 1, it's traveling at velocity v1. And I'm going to tell you a couple of other things. I'm going to tell you the distance along that inclined plane, okay? And that distance is d1 here. And I'm also going to tell you the angle that inclined plane is inclined at, and I'm going to call that theta 1, okay? So we have our first plane, distance d1, angle theta 1. The block starts off at velocity v naught, and it ends at velocity v1. Okay, now we're going to start at the top of plane number 2. Its initial velocity is v1. The final velocity of plane number 1 is the initial velocity of plane number 2. So the initial velocity here is v1, and it's going to travel a distance d2 at an angle theta 2 until it speeds up to velocity v2 there like that, okay? And so I didn't put any numbers in there, but you can assume that you had numbers or something like that and you could solve it. But we're going to do it without numbers because we're going to see a pattern arise as I put one inclined plane after another, okay? So the first thing we notice is if we do the free body diagram, and I skipped the details, and the reason I skipped the details is we've done so many of these right now up to this point that there's no reason to do it again. But just to remind you, there is a normal force this way, and then there was a gravitational force straight down, but the gravitational force broke into 2 pieces: the parallel to the plane and perpendicular to the plane. The piece perpendicular to the plane canceled the normal force, so it's gone, and the only thing that remained was the component of gravity parallel to the plane, and if you recall, that was mg sine theta. Only here I put theta 1 because the inclined plane is inclined at angle theta 1. Okay, so if you add up all of the forces, well, F normal and the force of gravity, all you would get is an F net of mg sine theta 1. Okay, so great, we have the total force, all right, from Newton's law. And so now we make use of, remember, after you get the total force, the net force, you make use of Newton's laws. So we're going to make use of the fact that F net must equal ma, but this is a along the first plane, so we'll call it a1, all right? And we have a formula for F net. It's mg sine theta 1. That's got to equal ma1 according to Newton's second law. The masses cancel out, and we have a nice little formula for the acceleration on plane number 1. Okay, so on plane number 1, a1 is going to equal g sine of theta 1. All right, you know g, well, 9.8 meters per second squared, and theta 1, I give that to you. So in principle, you could calculate everything on the right-hand side here, and that gives you the acceleration along plane number 1. All right. But that's not exactly what we wanted. We wanted the acceleration as a step to finding the final velocity at the bottom of the plane given the initial velocity. So let's go back to the diagram here, like that. In principle, you know V naught, that's your initial velocity, and I want to find V1. And you say, well, how do I connect V naught and V1 and using the distance and that angle there? And you actually don't need the angle for that, you just need the distance. And if you recall, that was one of our kinematic formulas. It was this one. V naught, okay, given V naught, we can find V1 using the formula V1 squared is equal to V naught squared 2 times A1 x minus x naught. Okay, so you might remember that from when I introduced 1D kinematics. I added a couple of subscripts here. So there I had V naught for the initial velocity, and I just had V without any subscript because we didn't need it there. But here we need it because it's the velocity at the bottom of plane number 1 and at the beginning of plane number 2. So we'll call that velocity V1. Okay, so that's the final velocity at the bottom of plane number 1. And then also, when I first introduced this, we just had one acceleration, so we called it A. But here we want to call it A1 because it's the acceleration down plane number 1. Okay, and then there was this x minus x naught, and that was the distance over which it traveled. But you know that distance. That distance is D1. Okay, because it depends how you want to put your coordinate system, but not that it matters. If this point is x naught, the initial position, that point is x1. x1 minus x naught, remember this is 1D kinematics, okay? That is just that distance in there, okay? So x minus x naught, that would just turn out to be D1, all right? And so for x minus x naught, I can replace D1, okay? And for A1, I can put in g sine theta 1, and I find that V1 squared is equal to V naught squared plus 2g sine theta 1 times D1. Okay, now you'll notice I have the brackets around g sine theta 1 because that was the acceleration. But let me rearrange this. I can certainly do that because we're just multiplying some factors here. Let me put the D1 and the sine theta 1 together. Okay, so if I put the D1 and the sine theta 1 together, this is going to look like V1 squared is equal to V naught squared plus 2g D1 sine theta 1. Notice all the subscript 1s are now together, and the subscripts are referring to the details of that incline plane. Okay, so you take a look at D1 sine theta 1, you go, what is that? What is this D1 sine theta 1? And if we redraw the triangle, D1 is the hypotenuse. Theta 1, that's the angle right in there. Okay, and H1 is the height. It's the opposite of theta 1. Well, the opposite of an angle is the sine. And so you can write that H1 is equal to D1 times sine of theta 1, like that. Okay, so that D1 sine theta 1, all right, it is the height of plane number 1, like that. And so I can take D1 sine theta 1, remove it, and just say H1, where H1 is understood as the vertical height of the drop. Okay, so that gives us an equation right there. Okay, and the equation says, look, the velocity at the bottom of plane number 1, the velocity there, is equal to, well, velocity squared, okay, there, is equal to the velocity squared up there, plus 2 times g, and you know g, times h1, and that's the height of that plane. Okay, that's the vertical drop. So in going from this point here to that point there, from the top to the bottom, it drops through some vertical height. That's h1. You know that in principle because I've given you all the details of this plane. Okay, I've got to give you the details of the shape of the plane, otherwise you wouldn't be able to do the problem. And so we got our first equation there. Now, we can do this for the second plane too. So here we are, we've got plane number 2, and I redrew it, but it's kind of silly to redraw because all it is the same thing, but with subscript 2 replacing subscript 1. And so we have D2, theta 2, and H2. Okay, a little tricky with the velocities. The velocity at the top of plane number 2 is V1, and the velocity at the bottom of plane number 2 is V2. And so going through the same steps as before, you're going to find that V2 squared is equal to V1 squared plus 2GH2. Okay, so it's the same form. Let me put the two equations side by side. These two equations are the same form. Okay, but the subscripts have been shifted because this equation here, equation A, refers to the first plane, whereas equation 2 refers to the second plane. Okay, now what? Well, what we really wanted is to express V2 in terms of V naught. That V1 is the problem. The reason it's a problem is because it's the intermediate velocity, and we don't know that in principle. So what we know, go back to this diagram here, or kind of what we've been asked for, is I say to you, look, I want to find V2, which is the final velocity at the bottom of both planes, in terms of V naught in any of the geometry of the path. Okay, I don't want that V1 in there. All right, because I don't in principle know V1. I know V naught. Okay, like in my very first example, I told you that the roller coaster started with V equals 0. So that in that case, V naught would be 0. And then I ask you, what's the velocity at the bottom there? But I don't tell you any of the details of the velocities in between. So that V1, we want to eliminate that. So if we take a look at our two equations here, oops, I went too far. Okay, we take a look at these two equations. You realize that you could take equation 1 for V1 squared and substitute it into equation A. In equation A, V1 squared, substitute it for V1 squared in equation B, and that would eliminate it. And that's what I did next. Okay, it's just a little bit of geometry. So I'm going to substitute for V1 squared from A into B. So I have V2 squared is equal to, the square brackets is where V1 squared was, but I've replaced it with equation A, plus 2GH2. And then, just rearranging the terms, which is pretty easy, I get that V2 squared is equal to V naught squared plus 2G H1 plus H2. You'll see the H1 there and the H2 there. They have the same factor 2G in front, so you could just factor that out. Okay, so we'll call that equation C. All right, now take a look here. I redrew the diagram. Okay, notice that I don't have to know V1 in order to calculate V2. What do I need to calculate V2? All I need to calculate V2 is V naught, the initial velocity, G, obviously, acceleration due to gravity, and what is H1 plus H2? It's the total vertical drop. It's the vertical drop across plane number 1 plus the vertical drop across plane number 2. Okay, and so this is kind of an interesting result. Let's think about this again. In order to get the final velocity at the bottom of both planes, I need the initial velocity at the top and the vertical drop, and that's it. The details of those angles in there, the details of, how fast V1 is going there, don't need them. They fell out of the picture, okay? Now, that's interesting in and of itself, but we could do this again and again and again. We can add a third plane, and then a fourth plane, and then a fifth plane, okay? And so what I'm going to do next is I'm going to say, look, imagine that we had yet another plane, plane number 3. In that case, the equation, like equation A, equation B, would lead to this equation D here, which would be V3 cubed is equal to V2 squared plus 2GH3, where H3 would be the drop across, the vertical drop across plane number 3. Okay, and just to remind you, V2, that's the velocity at the bottom of plane number 2, but it's the beginning, it's the initial velocity for plane number 3. And V3 is the final velocity for plane 3. Okay, so the final velocity for plane 3 is related to the initial velocity for plane 3 plus 2g times the vertical drop for plane 3. Okay, now we could take equation D and eliminate V2 with equation A, and if we do that, I'm just going to skip the algebra, it's kind of easy. We get this equation, which we can call equation E. Actually, let me scroll down a little bit more so you can see the plane there. Okay, so this is equation E here like that, and this is V3 squared. Okay, it's actually, let me scroll down just a little bit more. Okay, so you can't see that I named this equation E, but it's there. It says this is called equation E. V3 squared, that's the velocity at the bottom of the third plane, the velocity at the very bottom of the entire path. What's that going to equal to? The velocity at the very top of that path squared plus 2g times h1 plus h2 plus h3. And you go, what's h1 plus h2 plus h3? It's the vertical drop across all 3 planes. Okay, and guess what? You can do this again and again and again and again and again. All right, what is interesting about this is that the details of the path in between, they're totally falling out. Nowhere in here do you see theta 1, theta 2, theta 3. They're gone. Nowhere do you see d1, d2, d3. They're gone. Nowhere do you see v1 or v2. They also fell out. All you need is the initial velocity and the vertical drop, and that's it. And that vertical drop, it doesn't matter whether you went by this path or by any other path, because you could do this again and you could change your angles. I mean, I didn't put in numbers for the angles. So, you could do this again for any angle theta 1, for any angle theta 2, for any angle theta 3, for any distance d1, for any distance d2, for any distance d3, and you would still wind up with the same result. So, what is this telling us? What is this telling us? And just to be like, just to really push the point, I could do it for a fourth one, in which case you would have v4 squared is equal to v naught squared plus 2g h1 plus h2 plus h3 plus h4. What that's telling us, it's giving us this equation, which I called equation star, and that is that the final velocity squared plus is equal to the initial velocity squared plus 2g times the total vertical drop, independent of the shape of the path. Okay, and equation star, so this is the important point here. Equation star, this equation here, is independent of the path downhill. So what started off as a very difficult problem, okay, and that was, let me scroll right back up to the very first diagram here. The difficult problem was applying Newton's law along this entire curved path like that. Okay, and at every point you'd have to redo all of the recalculate F nat, recalculate A, and so on, and you'd have to do it along this complicated path here like that. It turns out you don't really have to do that, because the final velocity there does not depend on the path, the shape of the path there. It only depends on the initial velocity and that vertical height there. And that's an amazing result. Okay, now that is the conservation law at play. Okay, I haven't given you the conservation law explicitly. I've just shown you how a conservation law can take some really complicated problem like this, where you have this really bizarre curved path. Well, it's not that bizarre, but you can imagine that it could be a very complicated path, because roller coasters, they're more fun the more complicated the path is, okay, the track is. So, you could have this really complicated path, and yet you could still calculate the final velocity from the initial velocity with just one other number, the vertical drop. Okay, so there you go. There's the power of a conservation law. All right, let's scroll back down. And so this basically just summarizes what I said up above. So, all you need is that vertical drop in there. And to define the vertical drop very easily is, here's V naught. That's where it started. Okay, so I just put this dashed line there like that. And this is where it ended up. The vertical drop is just the distance there like that. Okay. And, when I say that the path could be anything, as long as the vertical drop is the same, the path can be anything. So here was my initial path, reproduction of my initial path. It could have been just a straight drop down like that. Okay. It could have been a drop along, some kind of like ladder like that, up and down, up and down, up and down. I'm sure if this were a roller coaster, that would make you pretty sick, going up and down like that. It could even have done this, which is go extra low, like below, like this is ground level here. I'm trying to show ground level along that line there. It could have even started up there, gone below ground level, and then come back up, and it would still be the same. When I say any shape, it really means any shape. Okay, now there I did sneak something here, which I will come up later. There's no friction, so in reality, it wouldn't quite be what I'm saying right now. But when I derived all of this, when I derived the equation star, I just assumed that there was just a normal force and the force of gravity. There was no friction. Okay, but friction will make things a little bit different. But that's for later. I just wanted to mention it now, because if your intuition in your mind is saying, I think that it would be different, your intuition is probably factoring in the friction. Okay, so remind you what a conservation law looks like. You calculate at some point in time some initial conserved quantity. You calculate at some later time a final conserved quantity, and what the conservation law says is that the initial conserved quantity and the final conserved quantity, they're equal to one another, independent of the details of the dynamics. Okay, so it doesn't matter how it went from the initial to the final. It doesn't matter the time. Okay. In fact, you can even reverse these in a lot of my problems that I'm going to do later. I have time going one way. You could run the entire dynamics backwards. Like imagine just running a movie backwards, and it would still work just the same because the final would become the initial and the initial would become the final, and the quantities would still be equal. This is basically what is meant by a conservation law. Okay. Calculate some quantity, some conserved quantity at some point in time, and it's the same value at all points in time. Okay, not just final, but it could be like 20 points of time. So again, back to my example of money being exchanged in the classroom, just to remind you, we've got so much money in our pockets and we're not going to destroy any money and no one's going to walk out of the room. No one's going to enter the room. So the amount of money, the total amount of money in our pockets remains the same. As we exchange money back and forth, if at any point I say, how much money is in the room? Say it's $1,000. The next minute I say, how much money is in the room? It's $1,000. The next minute I say, how much is in the room? $1,000. If we do this for 10 minutes, I say, how much money is in the room? Still $1,000. And so the total amount of money in the room remains conserved. In this case, as we'll see, the total amount of energy remains conserved. So there's our conserved quantity. And the reason you want to use conservation of energy whenever you can is the problems become a lot easier. Okay, so you can see how easy that equation star was. There you go. Those are the kinds of that's the kind of simplification you can expect from conservation of energy. All right, so before I throw conservation of energy at you, I actually need to um, give you a broader theorem, and it's known as the work energy theorem. Friction kind of messes everything up, okay? And so to really understand the relationship between energy or how energy works, we need this other concept of work, and then we can tease out the friction from the rest of it. Okay, so let me show you how that does. I'm not actually going to prove the work energy theorem. It requires calculus, and I could do it for the calculus students, but to be quite honest, the reason I don't do it is it just doesn't give any intuition. Whenever something doesn't give intuition, I tend to avoid it because, like, what good is it? And if you were physics majors, then sure, you would need to reproduce it. But in the absence of in the absence of having to reproduce the entire proof, it's just best to just get at the intuition. So let's try to get some intuition here into what's going on. Okay, so we had that equation star, which said that the final velocity squared was equal to the initial velocity squared plus 2gh, like that. Okay, where h was that total vertical drop. You look at that equation, you go, well, I don't know, like, what is a v squared? What does v squared even mean? Okay, well, h means something, but what's 2gh? What does that even mean? Well, what I want to do with this is I want to multiply through by 1/2 m. Okay, and if I do that, then that v squared there has an extra factor of 1/2 m in front, and then that v naught squared has an extra factor of 1/2 m v squared, like that, and then the 2gh becomes mgh, like that. Okay, and so this equation basically takes on this form, and let me put all the 1/2 mv squareds to one side. All right, like this. Okay, so I have 1/2 mv final squared minus 1/2 mv initial squared is equal to mgh. All right. Now this equation it's a little easier to make sense of than the original equation. Okay, it generalizes better. All right. So the 1/2 mv squared, we're going to call that something. We're going to call that the kinetic energy. Okay. So this quantity energy, which is conserved, it comes in a couple of forms. One form is kinetic energy, and it's the energy just because an object is moving. All right, and to calculate the kinetic energy of an object, you calculate 1/2 mv squared, like that. Okay, why the 1/2 you'll see, but the mv squared, that kind of makes sense. Okay, so energy is the ability to do work, which I'm going to define in a minute, but you kind of have an intuition into what work is, and the bigger something is, the more work it does. I mean, imagine a car colliding into something. Obviously, the bigger the car is, the bigger the mass, the more damage it's going to do. Okay, so think of the damage as kind of a measure of how much energy there is. So the bigger the car, the more damage it does. Conversely, the faster the car is going, there's your V, the faster the car is going, the more damage it does. So the bigger, more damage it does, the faster, the more damage it does. And the velocity actually comes in as a velocity squared, which means that if the car is traveling at twice the speed, it actually does 4 times as much damage. All right, and the reason for that is because the kinetic energy actually goes as the velocity squared. Now, I'm kind of stating these things, but these are experimentally verifiable, okay? So this 1/2 mv squared, this is called the kinetic energy, all right? We're going to also define the work because it's going to turn out that this mgh is going to be the work. The work due to what? The work due to gravity. Gravity is going to do work on, you think of it this way, gravity is doing work on, in the case of our roller coasters, gravity is doing work on our roller coaster car, and that's what's speeding it up. That's what's changing its kinetic energy. So the work done by gravity turns into change in the kinetic energy. That's the work energy theorem in a nutshell. So how do we define work? Each force that's acting on an object has a certain amount of work associated with it as that object moves. Okay, so I've only drawn one force on this thing. I called it FP, and there might be other forces acting on this, so don't worry about it. Just say FP, say the push. Okay, so or pull, force of some pull here like that, and this is a box here like that. And suppose that while I'm pulling with this force FP at some angle theta, the box moves from here some distance d like that. Okay, so once again we have a box here, and there's a force FP which acts at an angle theta to a displacement d like that. All right, and then we can say that the work due to force FP, because remember there are other forces, so each one of them will have their work, but just the work due to FP is given by this formula here. The work due to P is equal to FP times D times cosine of theta. Okay? Now, why that's a useful definition is a little hard for me to really show you without, again, some deeper mathematics, but it kind of makes sense. How much, like, think about it this way: how tired do you get? Okay, pushing something. Well, the harder you push, the more tired you're going to get. It's like how much work do you do is roughly proportional to how tired you get. The harder you push, the more you're going to get tired, the more work you do. The further you push, the more tired you're going to get, okay? And then the cosine theta is, look, if the thing is moving in one direction, you're pushing it perpendicular to it, you're really not doing any work on this thing at all, okay? It's moving on its own, and whatever force you're applying is really not contributing to the work done on the object at all, okay? You might say, well, why would the object move in direction D if I'm pushing in perpendicular to it? If theta here were 90 degrees, don't forget there are other forces acting on this, okay, which might constrain it to move along path D. Okay, so there it is. There's our definition. The work due to force P is equal to FP, the size of force P, times the distance over which it acts, multiplied by cosine theta, where theta is the angle between the force and the displacement. All right. Now, let's illustrate that by calculating the work done by gravity in the above problem. Okay, so that mgh turns out to be the work done by gravity, and you could see that because if I have a mass here like that, m, and you say, well, what's the force of gravity on that mass? Okay, now again, there might be other forces, but I'm not worried about those other forces. All right, so we'll just take a look at the force of gravity, and that's given by mg. Okay, now suppose that this object drops a distance h like that. By that formula that I just gave you, the work due to gravity is equal to the force of gravity, which is mg, multiplied the distance that it dropped, in this case it's h, multiplied by the angle between fg and d. Well, that angle is 0 because the two are parallel to one another, okay? So the force of gravity is down and it's falling down, okay? So that's 0. And so when you calculate the work due to gravity as an object falls a vertical distance h, it turns out to be mgh. Okay, so there's the work due to gravity as an object falls. Okay, now I didn't do this at an angle, but if you did this at an angle, it would still be the vertical distance here because it might travel a distance d along an angle, but it would still be a vertical distance h, just like we saw above. So the work due to gravity, irrespective of the path that it takes, the work due to gravity is just going to be mgh, where h is the vertical drop. Okay? Now, what about the work due to the normal force? Well, the normal force is normal to the displacement of the roller coaster car as it moves along the track. So because it's normal means 90 degrees. So when you go to calculate the work due to the normal force, cosine of 90 degrees is 0. And so there you go. The work due to the normal force is 0. So the total work on the car at every point along the path is basically the work due to gravity plus the normal force, which just turns out to be mgh. Okay, and so what I basically showed you right now is that the total work as the roller coaster drops its vertical distance is going to be mgh. That includes the normal force because the normal force contribution to um, has no contribution to the total work. Okay, so our equation, which we had above, basically can be rewritten as 1 half mvf squared. That's your final kinetic energy, which we can call ke final. Okay, so there's your final kinetic energy. I guess I could have called it just K because usually we use just one letter, but I kind of like KE for kinetic energy, so that's your final kinetic energy, minus 1 half mv naught squared, which is your initial kinetic energy. So this is your change in kinetic energy here. And what's that got to equal? Mgh, in this case, turns out to be the total work. Now, that is not a proof of the work energy theorem. It is an illustration of it. The reason it's not a proof is because I applied it to just this particular situation of, going downhill on a roller coaster. But you can prove this in general, and it's always true, no matter how complicated your motion is or whatever. If you can calculate the total work, and that is, as this object moves at every point along the way, there's a force and there's a displacement. You calculate the work due to this force, and you calculate the work due to all the forces acting on that object, and you add them all up. That's your total work. That total work is going to basically turn into the change in the kinetic energy. Okay, and so there it is. There's the work energy theorem. The total work done on an object is equal to the change in kinetic energy. It kind of makes intuitive sense. I know this is not the most rigorous proof, but it kind of makes sense. You push on an object, and what are you going to do? You're going to speed it up. Okay, but in terms of work energy theorem, you do work on an object, you're going to change its kinetic energy. Okay, now changing its kinetic energy, just to remind you, kinetic energy is 1 half mv squared. Changing its kinetic energy, you're not going to change the mass. It's not like the thing gets bigger because you do work on it, because you apply forces to it. No, the mass stays the same, so the only thing that can change is the velocity. Okay, so doing work on an object changes the kinetic energy. Changing the kinetic energy means a change in the velocity. So it's still Newton's laws, but a new way of talking about that roller coaster going downhill is gravity does work on the roller coaster car, and that changes its kinetic energy from the top of the track to the bottom of the track. Okay, so that's this new way of thinking about it. All right, well, we're almost ready to do some problems. Okay, actually I'm going to show you potential energy, and then we can do problems. But let's look at the units of work right now. So if you take a look at the units of work, that's the units of FD cosine theta, which is the formula. Basically, it's the units of the force multiplied by the units of distance multiplied by the units of cosine theta. Cosine theta doesn't have units, okay? So that's basically has no contribution at all. But you know that the units of force are newtons, the units of displacement are meters, and so you get that the units of work are newton meters, okay? Now, just to make that more a little bit more clear, a newton is a kilogram meter per second squared. That came out of a unit analysis of Newton's second law. And a meter, of course, is a meter. And so basically, the units of work are kilogram meter squared per second squared. Now, that's an awful unit to work with, okay? And so just like with Newton, we consolidated it together, and we created a new Newton. We consolidated kilogram, here it is. We consolidated kilogram meter per second squared into a Newton. Here we consolidate kilogram meter squared per second squared, and we call that a joule. And a joule is the unit of energy. Okay, so Joule is the unit of energy. It was named after Charles Joule, that we'll actually study next semester, because he actually discovered that heat was energy, and as a result, we named the unit after him in his honor. Okay, so great. That's 1/2 of the work energy theorem. How about the 1/2 mv squared? It better have the same units. Okay, so here we've got the units of mass, okay, and the units of v squared. Well, the units of mass are kilograms. The units of velocity are meters per second, but squared. So we got meters per second, but all squared. And so we got kilogram meters squared per second squared. And there we go. We've got a joule again. Okay. And so basically, I just wanted to show you that, not only to introduce the joule, but to show you that the units of the work energy theorem work out on both sides of the equation. Okay. Oh, and just as a quick illustration, MGH also has the same units, okay? Because units of M are kilograms, G, the units of acceleration due to gravity are meters per second squared, and the units of height are meters, and again, kilogram meters squared per second squared, which are joules. Okay, now, the work energy theorem is actually all you would really need to do these problems. But there's friction, and friction is weird when it comes to energy and conservation of energy. And so one of the things we like to do is just break apart the total work into two pieces. Now, the problems I did above, I didn't even have friction in there, okay? I don't want to introduce friction until towards the end because, like I said, it complicates things. So let's try to keep things as simple as possible. And so what we want to do is introduce this idea of potential energy, and basically potential energy is just a part of the total work done. It's the part of the work done that's not the friction part. And so you can think of the total work done, and this is in all situations, as being made up of two pieces. There's the piece which we can handle very easily, which is the work due to conservative forces. I'll tell you what that is in a minute. Plus the piece that's more difficult to work with, and that's the non-conservative forces. Okay, so total work is basically made up of work due to conservative forces and the work due to non-conservative forces. And you say, well, what's conservative and non-conservative mean? And it turns out that um, the work due to conservative forces are those forces which basically don't make energy go into um, go into heat. Okay, so heat, I don't want to go into too much about what heat is, but heat is something which we don't see very easily. And so as an energy, I mean, when a car is driving down the street, you can tell that it has kinetic energy because it's moving, but you really can't tell that there's a lot of energy in your tabletop because of heat. Okay, so the conservative forces, they're the forces that basically at the macroscopic level conserve energy. They show energy the same all the way through. Okay, the non-conservative forces, basically they're the forces which convert the energy into heat, which appears to disappear. Okay, it looks like that energy disappears, and people were confused about this until Joule came along, and then he said, no, 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 that energy is still there. You just can't see it. It's in heat. We call those non-conservative forces. Now, if that's a bit confusing, let's just think about it this way. There's only one non-conservative force, and that's friction. So basically, there's the total work, and the way you should think about it is the total work is made up of the work due to all the other forces plus the work due to friction. And again, the work due to friction, because it takes the energy and it hides it in a way that makes it look like energy is not being conserved. We'll have to wait till next semester to get the full story. But just for now, basically think of the work as being made up of the work due to all the forces except friction, plus the work due to friction. Where friction, what it does is it turns the energy into heat. Okay, so I did mention that here, but we'll come back to that. Now, again, skipping a lot of mathematics, it turns out that your conservative forces, they're path independent, okay, and just like you saw a minute ago, you don't have to worry about to calculate the work, you don't have to worry about the path to go from the initial to the final place. And so there, you can actually introduce this thing called a potential energy, okay? And there's an initial potential energy and a final potential energy, and the work due to the conservative forces can actually be shown to be negative the change in this potential energy. Okay, so what is this potential energy? Okay, like how do I think about it? I mean, all I did was just just make this statement, and it's not at all very clear what it is. And so the idea behind a potential energy is that it's energy which is in the object because of some configuration, okay, because of some kind of situation in which that object finds itself. And so again, the easiest way to really show you what potential energy is with an example, and this is the potential energy due to gravity. Okay, and in the potential energy due to gravity, you can imagine a block which is up here. okay, say at a height of 5 meters. So we have a 10 kilogram mass at a height of 5 meters here like that. And everywhere in space here, there's G, which is like a gravitational field. This is like gravity pulling down, okay? And then we have the block here at ground level. This is at h equals 0, okay? And so you could say, all right, well, let me calculate the potential energy. The potential energy at the top here is going to be mgh, and the potential energy at the bottom is 0. All right, and so you could see that the change between the initial and the final potential energy, that's just equal to mgh. And so you could write that the work due to gravity is just that change in potential energy, which is negative the final potential energy minus the initial potential energy. The final potential energy, it's at ground level, that's 0. The initial potential energy was the block up at some height, 5 meters, and that was, in this example, 500 joules. And so the work is 500 joules, okay? So the way to think about this is kind of like a bank account. That's the way I think about it. And so, you've got so much money in your bank account at one state, and then work is like a withdrawal, and then you've got so much money afterwards, okay? So it's basically like, when you withdraw money from, suppose you have $1,000 in your bank account and you withdraw $100, that $100 is like the work, and you started at 1,000, you went down to 900, okay? So your initial is 1,000, your final is 900, and the change there is the 100, and that's basically the work. Now my example here was really easy because I put the final the final position at ground level, which had a potential energy of 0. But you could imagine going from 5 meters to 4 meters, okay? And you say, well, how much work is done due to gravity at 5 meters? Well, you calculate the potential energy at the 5 meter mark. You calculate the potential energy at the 4 meter mark. Now they're not both 0, okay? Or neither of them are 0. You calculate it at 5 meters, you calculate it at 4 meters. The change between the two, that difference, that's the work, okay? So that's the usefulness of doing this potential energy, or introducing this idea of potential energy. Again, it's kind of like a bank account where, you have so much potential energy, and then, you might withdraw some of that potential energy, and that becomes work. Or conversely, you could do work on it and then increase, and that's like adding money to your bank account, okay? So the energy, the potential energy, is just how much energy is stored inside of the object. And I said a minute ago, configuration or situation. In this case, the configuration is the height, okay? The higher the object is, the more potential energy it has due to gravity, okay? The next thing, before I give you my next example, last thing, sorry, is that potential energy is always due to some force, okay? So here we have potential energy due to gravity. In a minute, you'll see potential energy due to a spring. Kinetic energy, there's only one type, 1/2 mv squared. The only thing that causes kinetic energy is the fact that the object is moving, and the kinetic energy is calculated as 1/2 mv squared. But potential energy, it depends. Is it potential energy due to gravity? Is it potential energy due to a spring? And next semester, we'll see that electricity also has a potential energy. Is it a potential energy due to electricity, the electrical force? And so any force that's out there can have a potential energy associated with it, except friction, okay? So back to this again. We're going to think of the total work as being the work due to conservative forces. That's where you have this kind of like storage mechanism, this potential energy, plus something which just kind of like is not a storage, okay? It's kind of like a sink. So if I want to continue on my bank account example, this would be like a bank account where for some reason your amount of money just goes, even without you withdrawing money, it just goes down. So, one day you have $1,000, the next day you have $900, the next day you have $800, and it just keeps going down and down and down and down. And you go, but I didn't withdraw money. I know, because friction came in there and it took some of it away, okay? It took it away and made it into something that we don't know about yet, which is called heat. So that's why we're kind of bracketing out the non-conservative forces, because I don't want to deal with them until the very end, okay? But for the conservative forces, they work exactly as I said. You have this kind of a storage, and that's your potential energy. So you can have a lot of gravitational potential energy, then you can lose some gravitational potential energy. That becomes work, which increases your kinetic energy. You can also start at the bottom, and then, you do work, and then you're kind of like, as you're lifting it, you're storing energy and potential energy. You say, well, I want that energy back. Great, let go. and it comes back. Okay, lift it up, you're storing the energy, let go, and it comes back. So that's what potential energy is. It's basically, as the name suggests, potentially can become kinetic energy. All right, and the formula that relates the two is basically the negative of the change of the potential energy is equal to the work due to the conservative forces. Okay, because the amount of money that you withdraw is negative the change. All right, don't worry about it too much. I'm going to rearrange this anyhow. Okay, so there's the concept of conservative versus non-conservative work. And let me just show you the spring, and then I'm going to eventually rearrange this into the conservation of energy formula. So here's another example, potential energy due to a spring. Okay, now I'm saying due to a spring, but remember it's potential energy due to some force, and the force is actually F is equal to kx, like that. All right, and this is what's known as Hooke's law, which you'll actually do in the lab. And basically what it says is, look, if you have this is like, I could think of it as a linear track. This is like a wall here. I've attached this spring to a mass here like that. Here's a mass M, like that. And this spring, it just has a certain equilibrium distance. It's like it's got a certain length. If I don't stretch the spring and don't compress the spring, it just sits at that length. And I'll call that x equals 0. That's equilibrium. Okay. Of course, that's got no potential energy because, the spring is neither compressed nor expanded. If you let go of it, it's not going to go anywhere. Okay. So there's no potential energy in this configuration. As I stretch the spring, as I stretch it, there's a force, right? Because if I pull it out this way, there's a force that wants to restore the mass back to equilibrium. As I stretch it out to the right, the spring wants to pull it back to the left, okay? And so I'm doing work. And the potential energy due to a spring turns out to be this formula. U is equal to 1/2 kx squared, okay? So I'm not going to prove that for you, but there it is, okay? So really what I should say here is the potential energy due to Hooke's law, or the Hooke's force, okay? But that's kind of an awkward way. I will just say the spring, or the force due to a spring, okay? Or just the potential energy due to a spring. And there's the formula. So now we have two potential energies and their formulas. The potential energy due to gravity, mgh. The potential energy due to a spring, 1/2 1/2 kx squared. 1/2 kx squared. Okay? And I should say something about the units here. First, what are the units of the spring constant? So the spring constant is k here, F is equal to kx. You might go, what is this spring constant? Because I'm just introducing it now for the first time. The formula basically says something like this. If I stretch something 1 meter, there's so much force. If I double the stretch to 2 meters, there's twice as much force. 3 meters, there's 3 times as much force. So the force and x, the amount that you stretch the spring, they're linearly proportional to one another. But the constant of proportionality, that's k. Basically, k is a measure of how much force it takes to stretch the spring by 1 meter. Okay, the bigger k is, the stiffer the spring is, the harder it is to stretch. So a big k would be very hard to stretch. A small k would be very easy to stretch. Okay, well, I mean, it's pretty obvious that the units of k are going to be newtons divided by meters, okay, because I would have to divide both sides by x, and so you'd have F over x, and that's newtons per meter. Okay, so there are the units of k. All right, and I just give you a couple of examples here. K is equal to 1 Newton per meter. That means that it would just take 1 Newton, which is not a lot of force. Remember, a Newton is like it's the weight of 1 kilogram has a weight of 10 newtons. Okay, so it's like the weight of a tenth of a Newton, or 100 grams, which is not a lot. Imagine that you have a spring and you just apply 1 Newton of force, and the spring stretches 1 meter. Okay, so that's a very weak spring. So 1 Newton per meter, K, is very small. A more typical K, something like your shock absorbers in your car. So you know that your car has these shock absorbers, which are springs, and when the car hits a bump, it'll compress the spring, and that compression takes a lot of force. And so you might have a spring constant which is 150,000 newtons per meter, and that means that it would take 150,000 newtons to stretch this thing by 1 meter. Now, your shock absorbers generally don't stretch 1 meter. They'd probably break if they stretch 1 meter. But remember, this is a proportionality. It just says if you were to stretch it a meter, it would take 150,000 newtons. But say you only want to stretch it 1 centimeter. Well, 1 centimeter, that's a hundredth of this, and that would be 1,500 newtons. So yeah, 150,000 newtons per meter, but that just means that it would only take 1,500 newtons to stretch this spring 1 centimeter. Okay, it's linear that way. All right. So great, now we've seen two potential energies, and now I can give you the formula that we'll actually use for our problems, and that is our conservation of energy. No friction, because we got to get rid of those non-conservative forces, okay? So if we start with the work energy theorem, which is true in general, okay, and we have that basically the total work done is going to equate to our change in kinetic energy, we now take the total work and we break it up into our conservative and non-conservative pieces. And the non-conservative pieces, we're just going to say 0 right off the bat. Why? Because we're just going to get rid of friction. So for our first set of problems, there's no friction, okay? And then for our conservative force, because they're conservative, they basically act like this storage system. And so basically your conservative force is just negative the change in the potential energy, all right? And so we get this equation here. Now, at this point, what I want to do is I want to put all the final stuff to one side and all the initial stuff to the other side. So if I have here a negative UF, I can bring it to the left-hand side, and that becomes a positive UF. And over here, I have a negative kinetic energy initial. I bring that to the right-hand side, and it becomes positive. And we get this equation here. And this is actually what we're going to be using, okay? It's a very intuitive equation, and it's exactly the conservation law that I mentioned right at the beginning. You can calculate the total energy at the beginning, and that's going to equal the total energy at every moment of time after that. And what goes into calculating this total energy? It has two pieces. One piece is the kinetic energy, and the other piece is the potential energy. The kinetic energy by itself is not conserved. And that's obvious because in my roller coaster example, the velocity is going up and down. It could be, if it goes up, the roller coaster goes up and down, then the velocity will actually go up and down too. Well, if the velocity changes, that means the kinetic energy is changing. So the kinetic energy is not conserved by itself. The potential energy is not conserved because it's mgh, and when h is big, there's a lot of potential energy. When h is small, there's little potential energy. So the potential energy by itself is not conserved. But the two together, when you add the kinetic and the potential energy together, what we will call as the total energy, E, the total energy is conserved, okay? Provided there's no friction. And this is what we're going to use for our problem solving, okay? So, I mean, it was a little conceptually demanding there. You might wonder, why did I introduce work? Well, because we're going to have to go back to it when we add friction. But basically, I had the work energy theorem, which said, the change of the kinetic energy is the total work. And then I had to say, you know what, there's this friction that's going to mess things up. If we just forget about friction, then we get this equation right here, okay? Because we have this storage mechanism with potential energy, and then this is what you get right here, okay? Conservation of total energy. And now we're ready for our first example. Okay, before I jump in and actually read the problem, this is basically our initial problem, but now I've added some numbers, or my initial example right at the beginning of the lecture. Okay, so here I have the roller coaster, okay, and I have some points A, B, C, D, like that, and I don't care what the energy is, okay, what the number is. This is what I can say. If I calculate the total energy at A, it's going to be the exact same number at B, it's going to be the exact same number at C, and it's going to be the exact same number at D. No matter what that total energy is, if I calculate it at A, it's the same at B, C, and D. Conversely, if I calculate the total energy at C, because maybe I have enough information to calculate it at C, the total energy at C, then I know what it is at B and A and D, okay? And because this total energy is conserved, it's going to constrain the problem in such a way that we can actually solve for whatever I'm asking for in the problem, okay? So it doesn't have to be the first one. You don't have to have the total energy at the first one and say then all subsequent one. If you can calculate the total energy at any one of these points, it's the same both backwards and forwards in time, okay? So great, let's do that. Let's do this problem. Okay, so just look at the numbers here because they're going to scroll off. A is 100 meters above ground level, B is 50, C is 75, and D is right at ground level, which I called H equals 0. Okay, so here, a roller coaster car, A roller coaster car starts at point A with an initial velocity of 5 meters per second. I just changed it. I just thought I'd show you, how you could have any initial velocity you like. Okay, so a roller coaster car starts at point A with an initial velocity of 5 meters per second. Find the total energy, the total kinetic energy, and the total energy, the kinetic energy, the potential energy, and the velocities at points A, B, C, and D. Okay, and the car has a mass of 500 kilograms, no friction. All right, so at each one of those 4 points, I want you to tell me what is the total energy, what is the kinetic energy, and what is the potential energy, and then finding what is the velocity. All right. Now, you don't have to do this in this order. Sometimes you'll know the total energy before you know the kinetic and potential. That's okay. As long as you get all four of those at those 4 points, that's all I'm asking for. All right. So let's do it. Let's start off at point A. It turns out that I did give you enough information at point A. So at point A, you say to yourself, okay, total energy. What's the total energy there? It's made up of two pieces. There's the kinetic piece and there's a potential piece. For the kinetic piece, there's only one way to calculate the kinetic energy. There's only one type of kinetic energy, and that is the energy because something is moving, and that's equal to 1/2 mv squared. Okay, so substituting in the numbers, the mass was 500, the initial velocity was 5 meters per second squared, and that turns out to be 6,250 joules. A joule is not a very big number. Okay, we'll actually talk about joules as food energy next semester. Okay, when we talk about heat, and so I'll make it a lot clearer how small a joule is at that point. But yeah, this is not a lot. 1 joule is not a lot. So 6,250 joules. We're going to convert that to 6.25 kilojoules. Okay, so remember the MKS unit is joules, but you will see kilojoules and you'll even see megajoules. Okay, so get used to switching kilojoules to joules and megajoules to joules. All right, so there's the kinetic energy, 6.25 kilojoules. That's not enough for the total energy. That kinetic energy is going to change. Okay, here's the potential energy, and you say to yourself, well, what contributes to the potential energy? Because remember, there can be many contributions. Okay, we know of two: the spring and height. Okay, well, there are no springs in this problem, so the only thing it can be is gravitational potential energy, and the formula for that is mgh. So here we have U is equal to mgh, and m is 500, g is 10, we'll approximate g as 10, and the height is 100 meters for point A, and you work that all out, and it turns out to be 500 kilojoules, much bigger than the kinetic energy. Okay, so there's your kinetic energy, there's your potential energy. What's your total energy? The sum of the two. And when you add the two together, you get 506.25 kilojoules. Okay, now just to be complete, I did ask you for the velocity at point A. That's obvious because I gave it to you. I told you that it was 5 meters per second. So there you go. At point A, we have all four pieces of information we want: kinetic energy, potential energy, total energy, and the velocity. Great. Let's move on to point B. Now, point B, if I asked, do you know the total energy? The answer is yes. You didn't have to calculate anything. You know that because, remember, there's no friction here. Energy is conserved. Total energy is conserved. Total energy is conserved. We just found that the total energy was 506.25 kilojoules. That's not going to change. That's going to be the same at C and at D and at every point in between. It's 506.25 kilojoules. Okay, but the other two pieces are going to be different. And then you say to yourself, well, did I give you enough information to calculate the kinetic energy at point B? And the answer is no. If we go back to the diagram here, you really don't know what the velocity is at B here. In fact, that's one of the things you want to find. So if you don't have the velocity, you can't calculate 1/2 mv squared. So you don't know the kinetic energy at B. But you can calculate the potential energy at B due to gravity because you know the height. Okay, so over here, we do the potential energy is equal to mgh. M is 500, G is 10, the height is 50, that gives you 250 kilojoules. And now you say, well, what's the kinetic energy? Well, the kinetic energy plus the potential energy must equal 506.25. In other words, the kinetic energy has to be such that the total energy is 506.25. So the total kinetic energy must, the kinetic energy must be the total energy minus the potential, which gives you a kinetic energy of 256.25 kilojoules. Okay, so there's the logic. All right, you had the total energy, not because you calculated the total energy at B. I think this is one of the things that students find a little bit difficult in solving these problems. They're really simple conceptually, and maybe that's the thing, because they're so simple. You kind of miss the subtlety of it. And if you've calculated the energy at any point, that's it. You're done. Yeah, as far as the total energy, it's the same all the way through. So you have the total energy. And I didn't give you enough to get the kinetic, but I gave you enough to get the potential. You know that the kinetic plus the potential must equal the total. So you've got the total, subtract the potential from it, and that tells you what the kinetic must be. Okay, in this case, the kinetic energy is 256.25 kilojoules. All right. Now, the last thing I asked you for, because I asked you for four things, was the velocity. And you know now that the kinetic energy is 256.25 kilojoules. Convert that to MKS, 256,250 joules. What's that got to equal? Well, kinetic energy by definition is 1 half mv squared. So that's got to equal 1 half. M was 500, and the V we didn't know. But now you can solve for V. V turns out to be 32 meters per second squared. Okay, so that's how you solve this problem here. All right. Think about this again. Like, don't forget the bigger picture here. You really didn't need a lot of information about that track. All you needed to know was that you started off with a velocity of 5 meters per second at 100 meters height, and you dropped to 50 meters height. From that, you can calculate how fast this thing is traveling at point B. Okay, so you're getting an answer with very little information, and that's what makes conservation laws very powerful. All right, so great. Before we move on, always ask yourself, does this number make sense? Well, at the higher level, it was traveling 5 meters per second. As it went downhill, you expected to speed up. It did. It went from 5 meters per second to 32 meters per second. Great. Okay, let's look at point C. What's the total energy at point C? Still the same. Okay, 506.25 kilojoules. I didn't give you enough enough information to calculate kinetic energy, but I did give you enough information to calculate the potential energy due to gravity. And so the potential energy due to gravity is mgh. Plug in all the numbers. It's the same as above, but it's 75 now meters high, and that gives you 375 kilojoules. And if you work out the kinetic energy by just subtracting the potential from the total, you find that the kinetic energy is 131.25 kilojoules. So great, now that you have the kinetic energy, you can use the fact that the kinetic energy has to equal 1 half mv squared, solve for V, and you get 23 meters per second. And does that make sense? Well, let's go back to the diagram again. We start up here at the top at 5 meters per second, very slow. We drop, and now we're traveling 32, but then we start to go back uphill, and as we go uphill we lose speed, and so we go from 32 until we get to the top here at point C, and now we're only going 23 meters per second. Okay, great, that makes sense. Okay, and so we're done with point C, and now let's move on to the last point, which is point D. At point D, things become very easy because you're at ground level. The total energy is the same, doesn't change. You're at ground level, so you've spent all of your potential energy, okay? And so all of your energy has now gone into kinetic energy, and you can calculate the velocity because the kinetic energy has to equal 1 half mv squared. You know M, solving for V, you find that it's traveling at 45 meters per second at the bottom. Okay, and I just converted it to kilometers per hour to give you an idea how fast that is, because this is kind of a realistic example. 100 meters is about 300 feet, and roller coasters, they can go up to about 300 feet. That's a little high, but you know, that they can do that. And so by the time that roller coaster car is at the bottom of the hill, it's traveling at 162 kilometers per hour. Okay. So there we go. Let's go back to the diagram one more time, and let's see if we can get some intuition into what's going on here. At point A, the total energy, think in terms of total energy, and think of what the contributions are to the total energy from the kinetic and the potential. Okay, so at point A, almost all the energy is potential. There's a little bit of kinetic, but it's almost all potential. As it goes downhill, the potential energy decreases, but the kinetic energy compensates and increases. Okay, and so over here you've got less potential energy than you did at A, but more kinetic energy than you did at A. as you start to go uphill, some of that kinetic energy gets converted back to potential energy. Okay. And then finally, when you come down to the bottom of the hill, all of the potential energy is gone and it's all become kinetic energy. And so the way to think about this is it's kind of like one way that I think about it is like I have two glasses and I have water in the glasses. Okay. Now the total amount of water is the same. I can slosh the water from one glass to the other. I can pour one water from one glass to the other and then back again and then back again. The total amount of water remains the same, but the proportion that's in one glass might change. Okay. But the other one has to compensate for it. So A, almost all potential. B, roughly half and half kinetic and potential. C, more potential, a little less kinetic. And at D, all kinetic energy. And that's the way to think about these problems. Okay, it's like there's a total energy, and how does the energy slosh back and forth between kinetic and potential, kinetic and potential. Okay, um, all right, there's that problem. Let's do another problem. Okay, so this one's a little bit more interesting. Here we have a car and it's at ground level. So ground level I'm going to take as h equals 0 like that. And my car has a mass of 100 kilograms, sorry, 1,000 kilograms, 1,000 kilograms. Okay, I have a Honda Fit and it's actually very close to 1,000 kilograms. So this is a realistic number. And I'm traveling at 160 kilometers per hour, which is pretty fast. Okay, speed on highways about 100 kilometers per hour. So I'm traveling at 160 kilometers per hour. And I pass this point A, and then I encounter this hill and I go uphill 50 meters. Okay, so at point B now I'm at 50 meters above ground level. You know already what's going to happen. Some of the kinetic energy is going to become potential, so the velocity at B is going to be slower, as you expect. But then I've got this really interesting situation where my car slams into this spring here. And this is a heavy duty spring, and what the spring is going to do is as it compresses, as the car compresses, pushes up against the spring is eventually going to bring the car to a halt. Okay, and so there's the situation. You can read the English here. A car of mass 1,000 kilograms is moving at 160 kilometers per hour at ground level. That's point A. It goes uphill 50 meters. How fast is it going at point B? It hits a shock absorber, which brings the car to a halt in 3 meters. So I tell you how much the shock absorber compresses and how stiff is the shock absorber. In other words, what is K? Okay, whenever I say how stiff is the spring, I'm really asking for the spring constant K. Okay, so let's solve this. All right, so there are 3 points to consider. Now, I didn't tell you where to calculate the energy. I didn't even tell you to calculate the energy. What I'm asking you, just to look at the problem again, is how fast is it going at point B? So I'm asking you for a velocity at V, and I'm asking you at point C. At point C, I'm asking for K. So it's not at all clear that you need energy here. But, if you think about it, energy is really going to help us solve this problem. So you look here at these 3 points, A, B, and C, and you ask yourself, did I give you enough information to calculate the energy at C? And the answer is no, because you don't know K, so you can't get the spring constant. You don't have the spring constant, so you can't get the potential energy to the spring, and so on. And you don't know the total energy at B because you can't calculate 1/2 mv squared there. You can't calculate the kinetic energy, and that's because you don't know the velocity there. But at A, there is no potential energy. There's no potential energy due to gravity because it's at ground level. There's no potential energy due to the spring because we haven't hit the spring yet. Okay, the spring's not even in the picture yet. And so all the energy is kinetic, and you have enough information to calculate the energy, the kinetic energy, because you have the mass and you have the velocity. So let's start off by calculating the total energy at A. All right, so here I say we can find the total energy E at point A. The total energy is the kinetic plus the potential. Okay, the kinetic is calculated as 1/2 mv squared, and the potential is 0. And we know that because there's no gravitational potential energy. You're at h equals 0. So if you calculate mgh and h is 0, that's 0. And there's no spring potential energy because the spring hasn't been compressed yet. You're nowhere near that spring. So x for the spring is 0. So the spring potential energy is 0. Okay, and so there's no potential energy there like that. Okay, so the total energy is all kinetic, and plugging in the numbers, m is 1,000, v is 45 meters per second, and so you get that the total energy of the car is 1,012,500 joules. That's roughly 1,000 kilojoules, if I move the decimal over 3, or 1 megajoule. Okay, so a car traveling at 160 kilometers per hour has a 1 megajoule of energy. A megajoule is quite a bit. You can imagine how much how much damage a car traveling at 160 kilometers per hour, how much damage that would do, and that's roughly what you should think of as 1 megajoule. It's like a little explosion, something like that. Okay, so great. We have the total energy at point A. All right. Now let's turn our attention to point B. At point B, I want the velocity. Okay, so let's see how we can do that. We know that the total energy is that 1 megajoule number here, like that. Okay, so we know the total energy is 1 megajoule, but that's not the end of the story. That's the beginning of the story. You say, well, what contributes to that 1 megajoule? What adds up so that you get that 1 megajoule? Well, there's two pieces here. There's the kinetic energy and the potential energy. There's kinetic energy there because the car is moving. There's potential energy there, gravitational potential energy, because it's uphill. So back to the diagram here. See, the car went uphill 50 meters. So it's higher up. And if it's higher above the ground, 50 meters above the ground, there's a gravitational potential energy associated with that. Okay, so there's a gravitational potential energy, and that's mgh. And there's no spring, not yet. We're on the top of the hill, but we're still not at the spring, so no potential energy due to the spring. Okay, the total potential energy, maybe I should have stated this earlier, but the total potential energy is the potential energy from every contribution. You can have potential energy due to gravity and potential energy due to a spring all at the same time. Okay, and so here we just have potential energy due to gravity. All right, and plugging in the numbers, we have everything except for the velocity, because remember, that's what we want to find at point B, the velocity. So the mass is 1,000, g is 10, the height is 50 meters, and we work that out, and we find that, skipping some of the algebra, which is pretty easy, we find that the velocity at the top of the hill is 32 meters per second at point B. Okay, does that make sense? Well, we were doing 45 at ground level. Back to the diagram again. We're doing 45 meters per second. That 160 kilometers per hour is 45 meters per second. Okay, and we slow down to 32. Okay, so oh yeah, I forgot to mention here, 162 kilometers per hour is 45 meters per second. Okay, so easy conversion. All right, great. Now at point C, all right, we know the total energy there. The total energy there is still that 1 megajoule. That's not going to change, okay? But ask yourself again, what are the contributions to that energy? And so there's always a kinetic and a potential, and let's take a look here. The kinetic, I didn't even write it in. It's 0. Why? What does the spring do? The spring compresses and brings the car to a halt. If the car is at a halt, the velocity is 0. If the velocity is 0, the kinetic energy is 0. Okay, so there's no kinetic energy. What about potential energy? There's 2. It's still at the top of a hill. It's still 50 meters above ground level, and so it still has gravitational potential energy, mgh, and that's this term right here. But in addition to that now, it has a potential energy due to the spring, and here it is here, 1/2 kx squared. Okay? So the potential energy due to gravity plus the potential energy due to the spring, and there's no kinetic energy, the sum of that must equal that 1 megajoule. All right, now let's plug in the numbers. We know everything except for the spring constant, which is what I'm asking you to calculate. And so here we have, m is 1,000, g is 10, h is 50, 1/2, k we don't know, so just leave that variable alone. X I said was 3 meters. The spring compresses 3 meters and bringing car to a halt, and that's got to equal that 1 megajoule number right there. Now, algebra is pretty simple. Okay, this is 500,000 plus 1/2, 9, and 3 squared is 9, times k is equal to that, and it turns out that k is 114,000 newtons per meter, or 114 kilonewtons per meter. And this is not an atypical number for something like a shock absorber. Okay, something that's fairly stiff. All right, and so there you go. That solves this problem. All right, so don't know what else to say about this, but maybe we should just look back at it and think about how the contributions to the energy slosh back and forth. At point A, all the energy is kinetic. At point B, some of the energy is kinetic, some of the energy is gravitational potential energy. At point C, that's after the spring is compressed, there is no kinetic energy left. There's still gravitational potential energy because it's 50 meters above ground, and there is a spring potential energy. So at point C, the energy is potential energy due to gravity plus potential energy due to the spring. Okay, so that's how the energy sloshes back and forth. The total being 1 megajoule all the way throughout at every single point along the way here. All right, next example. Okay, so here I have a mass which is 5 kilograms, and it's sliding along this frictionless surface. Unfortunately, we can't introduce friction yet. We have to do non-conservative. We have to bracket out non-conservative forces. So this block is sliding along a frictionless surface like that, and it goes uphill from point A to point B. There like that, and by the time it gets to point B, it stops, and at that point, it has a height of 7.5 meters. Okay. I don't tell you the initial velocity. That's what I want you to calculate. All right, so there's the picture. Let me read the English here. A mass of 5 kilograms encounters a hill and goes up it, a vertical height of 7.5 meters before stopping. Okay, so it goes up 7.5 meters before stopping. That's point B. Assuming the ground is frictionless, so all the way along it's frictionless, how fast was the mass moving at point A? All right. So again, this problem is asking to be solved using conservation of energy, if for no other reason, because I don't tell you any of the details of the shape of the hill, and even if I did, it'd be just a pain to try to do it, by breaking it up into a bunch of little incline planes there. Now this is this problem is solved using conservation of energy. And so as soon as you say, oh, I'm going to use conservation of energy, you ask yourself, well, where can I calculate the total energy? You can't calculate the total energy at A because I didn't give you the velocity at A. So you don't have the total energy here, but you can calculate the total energy at B. Now, it doesn't matter that B is at a later time. As long as you can calculate the energy at any point along the path, that's the energy at every point along the path. So find a point where you can calculate the energy, and that's the energy everywhere. Okay, so can we calculate the energy at B? Yes, we can, because the energy at B is all gravitational potential energy. It stops there, so there's no kinetic energy. B is equal to 0, so all the energy is gravitational potential energy, mgh. All right, great. So over here, we'll start with point B. We have enough info to find energy at B, at point B. And so we have the energy is equal to 1/2 mv squared, the kinetic, but that's 0 because it stops there, plus mgh. Well, just substitute in all the numbers for mgh. M is 5, G is 10, H is 7.5, and that tells us that this block has 375 joules of energy all the way along the path, okay, including at point A. So at point A, the energy is 375 joules, and you ask yourself what contributes to that energy at point A, and it's all kinetic energy at point A because there's no gravitational potential energy there at all. Okay, so I just went directly and took the energy and just wrote 1/2 mv squared. Again, you have to ask yourself what contributes to the energy there. And the only thing that contributes to the energy at point A is kinetic. And so it's 1/2 mv squared must equal the total energy. And then solving for V is very easy. It's 12.3 meters per second. Okay, so this was an easier problem than the previous one. But what I wanted to show you is that don't just go to point A and say, oh, I have enough information to calculate the energy there. Not necessarily. You might have to look at some other point. There might be some other point in the problem where you have the total energy. But knowing that there's no friction, energy is conserved. And so if you find the energy at one point, it's that energy at every point along the path. Okay? All right. So I'm just going to show you a few variations. We won't actually solve these, just to get your mind going. Same kind of idea here. Suppose that I give you both x and k at point C. So this is like the problem where the car is going uphill 2 problems ago. And this time, rather than telling you that how fast it's going at point A, I ask you what's the velocity at point A and what's the velocity at point B. But what I do is I tell you the spring constant, and I tell you X, how much the spring compresses at point C. Well, if I tell you the how much the spring constant compresses, how much the spring compresses, that's X, and I tell you K, you've got the potential energy due to the spring here. But you also know the height because they give you that 50, so you have the potential energy due to gravity there, and there's no kinetic energy there. So in this example, you would have all the information to calculate the energy at point C. Whatever that energy is, it would be the same energy at point B and the same energy at point A. Now at point B and point A, the only unknown is the velocity, and so you'd be able to just set the, over here, let's do A first. Here the energy is all kinetic. Whatever the total energy is that you got at C, you say, oh, it's all kinetic energy here, so 1/2 mv squared is equal to that total energy, and that would give you the velocity at A. The velocity at B, though, is a little bit more complicated because you have two contributions here. You have the kinetic energy 1/2 mv squared, and you have the gravitational potential energy, okay, mgh. But you can calculate mgh completely, and the only unknown is V, but when you set that 1/2 mv squared plus mgh equal to the total energy there, you'd be able to solve for V. The only reason I wanted to show you this variation is because I could have done that same problem, but rather than giving you enough information to calculate the total energy at A, I gave you enough information in this variation to calculate it at C, and you'd have to work backwards. Don't think about the time here. Don't say, oh, it's at point A first, and therefore I have to calculate the energy at A, and that's carried over to B and C. No, no, no. You can, if you find one point where you can calculate that energy, in this case C, you can use that backwards in time as well. Okay, so not exactly a subtle point, but I just kind of wanted to emphasize it, and that's what I basically said there. Okay, here's yet another variation. This variation is basically was inspired by a pinball machine, and so here what I have is a mass, and it's a block on a frictionless surface again, and we can't do a ball because balls rotate, and we'll talk about that when we get to rotational motion. But you know, we could just think of this as a pinball machine where you have no friction, and basically you have a block here. And if you've ever played pinball, how do you get the pinball going? Well, you've got a spring, and that spring pushes it forward. So here I have a spring which has been compressed, and that spring will then expand, and in expanding it will give it a kinetic energy, and then it'll go uphill to a certain height like that. Okay, and I could ask you to find the velocity at point C, and then also find the height of point B. Okay, if I give you all the information to calculate the energy here at point A, then you could calculate the velocity at C and the height at B. So more specifically, how would you think about this? Think about what contributes to the energy. What contributes to the energy at A? There's no kinetic energy. There's no gravitational potential energy because it's at ground level. So all the energy is where? In the spring. It's all spring potential energy. So the total energy here is 1/2 mv squared. Sorry, 1/2 kx squared. 1/2 kx squared. Over here at point C, the spring has been expanded. There's no gravitational potential energy because it hasn't gone uphill yet. There's no spring potential energy because the spring has been sprung, it's expanded, and so all the energy is kinetic, and so here the total energy would be 1/2 mv squared. Over here, the block has gone uphill, it stopped, okay, so there's no kinetic energy up there. There's no spring, that's out of the picture, so there's no spring potential energy. It is all gravitational potential energy, okay? And so the energy at A, B, and C, the total is the same, but look at what's happened here. At point A, all the energy is spring potential energy. At point C, all the energy is kinetic energy. And at point B, all the energy is gravitational potential energy. So that's kind of interesting. You can see all three of those energies at play, okay? You know, again, spring potential, all kinetic, all gravitational potential, all right? And in between here, like if I asked, say, at a point D here, which was halfway up the hill, you say, well, what's the energy there? Well, it would be partially kinetic and partially gravitational potential energy, kind of like we saw in our roller coaster example. Okay, so I didn't do any numbers here. I just more or less wanted to show you this because I would just want you to think in terms of of the energy kind of sloshing back and forth between its different forms. Okay, so the basic sloshing is between kinetic and potential, but even potential, there are different types of potential. So you can have gravitational potential and spring potential, and so you can have energy sloshing back and forth between spring potential energy and gravitational potential energy. As long as the total adds up to the same amount as everywhere along the path, energy is being conserved. And so here at the very bottom of the paragraph, I say, look, at point B, all the energy is spring potential energy. At point C, all the energy is kinetic energy. And uh, and oh, wait a sec. My points are in a different. Yeah, I'm sorry. There's point A, point C, and point B, so they're not quite in order. Point A is all spring potential energy. Point C is all kinetic energy, and point B is all gravitational potential energy. You can see the energy sloshing back between the two. Okay, so we haven't done friction yet, but that's coming up. Okay, so that's the end of our lecture. Thank you very much.